My project is about deep learning on Spark. Let's briefly touch on some basic concepts involved in this project. Deep learning. Deep learning is part of machine learning, and it's based on the neural net model. Basically, it is built by combining and recombining a limited set of neural net layers to come up with an even more complex model. The evolution of artificial intelligence and cognitive applications and the readiness of big data in most of industrial domain are the driving forces for deep learning's popularity. Another concept is Spark. Spark is a fast distributed data processing engine. Comparing with Hadoop MapReduce, it provides a fast in-memory approach and easy grasp API. The figure here shows the typical structure of a Spark cluster. Spark master node runs a Spark master process as well as a driver program. We also have a number of Spark worker nodes, each running an executor process. Spark has a cluster manager such as Yarn, Mesos, which are used to distribute resources within Spark cluster. Let's go back to our current problem statement. The dataset we are using here is ImageNet 2012 Challenge dataset, which is an image reservoir, contains over 10 million image URLs. If we process the whole dataset with a pre-trained inception deep learning model to obtain the image inference using a single CPU environment, it potentially will take 10 years to finish the whole job. So will Spark be the perfect fit to reduce the computational time and improve the performance in this case? The graph here shows how we are going to apply Spark to this particular image classification problem. On Spark Master, we run driver program. The driver program will load the inception TensorFlow graph model from the destination file via protocol buffers. We also need to process two mapping files to get the UID and human readable synset string relationships. And the graph model will be deployed to each worker node. And the cluster master will parallelize ImageNet dataset, and each node handles a partition of dataset. After the processing is done on each worker node, the result will be collected back to the master. Okay, next step, let's dig deeper into how we are going to use Spark API to achieve this. The first thing we need to do is to set up Spark Contact. Spark Contact is a main entry point for Spark program. It's the connection to Spark cluster. Since we plan to use Spark Submit to launch our driver program, instead of using Spark Shell, we can simply define Spark Contact just with application name as its parameter. Spark also has a broadcast variable, which is a read-only variable. They are created from the driver program and made available to the worker nodes when worker starts executing the computation. It can access the broadcast variable just by calling the variable.value. we use broadcast API to give worker node access to both the inception TensorFlow model and also the mapping list we created in the driver program. The image URL collection will be parallelized into RDD. And we also use a flat map to get a flattened RDD by performing a image classification transformation on the image URL collection RDD. Since in this project we care more about the final computation time, we use count instead of collect to trigger the distributed computation executing action. By the end, we need to call Spark contact stop to deactivate our Spark contact. We run Spark submit command, and here we define deploy mode as client, so Python program is launched on master instead of on worker node. Also, we define master as yarn according to the configuration in Amazon EMR. By far, we pretty much get the script ready. The next thing we need to do is to set up our Spark cluster. We use Amazon EMR, Elastic MapReduce, to set up our Spark cluster. They provide the console UI for us to follow the steps to build up this Spark cluster. So here we simply pick our application to be installed as Spark 2.1.0. And also in the hardware configuration, we pick the R3 X large as the hardware instance type. Since in this image classification case, we need a large memory. We can also define how many nodes we want to be included in this Spark cluster. In this case, we pick 5, 1 master and 4 worker nodes. And next, we pick the generated key pair to be used in SSH. After click on create cluster, EMR will start provisioning and bootstrapping the configured cluster. When the cluster ready, we can check cluster setup by using the nodes of a cluster UI. So here we can see for this 4 worker nodes cluster, each node has 22 GB assigned, and they all have 8-core CPU. Since we are using TensorFlow framework in our script, and it is needed in both master and worker node execution, we need to further install this package onto all Spark nodes. So we SSH into master node using our PAM file, and then we just use Python pip install to install the TensorFlow package on the master node. And then we can use the same PAM file to SSH into each slave nodes from the master and follow the same steps to install TensorFlow package onto every worker node. When everything's ready, we can start running Spark submit, and the Spark UI provides an interface to monitor the execution process. Since we have 8 core worker nodes, we can see here that we have 8 active tasks running at the same time on each node. Totally, we have 32 tasks being processed in parallel. So this screen shows the final job status for this 4 nodes cluster. So we can say the duration we take to process the whole job is 17 minutes in this case. And it also lists all the jobs has been run. So in this project, we also spinned up another 2 worker node Spark cluster to process the same data set. So this is the executor profile for this 2 worker node cluster. It has the same memory being it has the same memory being assigned, like 22 gigabyte and 8-core CPU for each node. And here is the executor profile. So we can say we have 16 active tasks running at the same time. Okay. And these slides, we put the final job status side by side to make a comparison between the 4 worker nodes cluster versus 2 nodes cluster. It shows 2 node cluster takes 32 minutes to finish the input dataset processing, while 4 worker nodes cluster only takes 17 minutes to process the same dataset. And the bar graph here just to present this computational time comparison result. Obviously, there is a linear relationship between the number of Spark worker nodes and the final computation time. Doubling the nodes number will cut the computational time into half. Note here, we didn't apply the original ImageNet dataset with 10 million URLs in this project due to the resources we have here. We split the data and only process the 10,000 URLs in this project. However, we proved if we can build a Spark cluster large enough, we can process the original dataset in a quite reasonable time. So for our use case, Spark is proved to be perfect fit. However, there are a lot of neural network models. They cannot be deployed onto distributed computer clusters. Doing neural net model training with a distributed system is a hard problem in the field. Another use case can use Spark to improve the performance and the computational time. It's model parameter training. So the basic idea is we parallelize the data and deploy the model with different parameters onto different worker nodes. After each training, worker will send the trained parameters back to the master, and the master node will average the parameters together and find the best set of the parameters, which will be used in next iteration. So from this project, we can see that the Spark definitely plays a very important role in the deep learning field. Okay, thank you.